Well, this is my first class on organic chemistry. Introducing organic chemistry. This is the first chapter of Cambridge Organic, and it's a very important chapter. Well, first of all, we need to recall about the molecular formula and empirical formula. We have already learned it in O level. Molecular formula will express the actual number of atoms present in a particular molecule. The examples are given here. In ethane, there are 2 carbon atoms and 6 hydrogen atoms present. So the molecular formula of ethane is C2H6. Here we do not get any idea about the arrangement of the atoms, but we can understand the actual number of different atoms present in a particular molecule. Empirical formula does not show the actual number of atoms present in a molecule. It expresses the ratios of the different atoms present in a molecule. If we compare the molecular formula and empirical formula, molecular formula of ethane is C2H6, but its empirical formula is CH3, as it is the simpler ratio of ethane, C2H6. Well, then what is about displaced formula? Displaced formula will show the arrangement of the atoms present in a molecule. It shows all the bonds present in a molecule. For example, ethane C2H4. Its displaced formula can be shown in this way. Ethane is an alkene, so it has double bond present between 2 carbon atoms. And there are 4 carbon hydrogen bonds present in ethene molecule. So all the bonds are shown in this particular type of formula. That means from displaced formula we can understand the arrangement of the atoms present in a molecule. Here example of ethanol and methoxymethane are also shown. Well, I'm going to change the slide now. Then what is about structural formula? Structural formula will not show the bonds. Here in the first example, you can see the formula of 2-chloropropane. Here the bonds are not showing. So bonds will be omitted, but in some cases we can show double bond or triple bond present in a molecule. If any double bond or triple bond present, it's not mandatory to show this double or triple bond in structural formula. So the idea is structural formula will not show any bonds, but we can write down the different atoms present in a particular molecule side by side in this way. So the displayed formula of this 2-chloropropane is showing just below of this structural formula. Displayed formula, as I already mentioned will show all the bonds present in a molecule. Well, let's try to identify structural formula from the displayed formula. A displayed formula is showing here. Now, which one is the structural formula of this molecule? Here the formula is, we can see CH3, CH2, then oxygen, then CH3. So if we try to match the structural formula with this displayed formula, the correct answer will be this one. Again, for this molecule, the correct structural formula will be the first one. Let me try again. Here, the correct structural formula of this propanol molecule will be this one. Well done. Well, I'm gonna change the slide. Now this is a new kind of formula with which we are not familiar with, skeletal formula. Skeletal formula is a very interesting type of formula. Here, all carbon and hydrogen atoms will be omitted. Let's see this example at first. 2-chloropropane. So first of all, we have to give a point. If we want to start a line, we have to give a point. That means a carbon atom is present with that point. Then we have to stretch the line up to another point. That means another carbon is present at the another corner of this line. So we can see this displaced formula contains 3 carbon atoms. So we can start with from here, first carbon, then we have to stretch it up to second carbon. Excuse me. Then as it contains 3 carbon atoms, so we have to stretch the line towards another direction to show that 3 carbon atoms present in this particular molecule. Then except carbon and hydrogen, another atom like chlorine is also present. Chlorine is present with the second carbon. So to show the location of this chlorine atom, we have to put another line with the second carbon and we have to show this chlorine atom. Skeletal formula will omit carbon and hydrogen, but if any other atoms or any functional group present in a particular molecule, that must have to be included in a skeletal formula. You can practice it at home. Another example of drawing skeletal formula is also given here. You can see this is a branched hydrocarbon. So 1, 2, 3, 4, 5. 5 carbon atoms present in this straight line. So let's start drawing this molecule. So we have to start from here. First 1, 2, 3, 4, 5. Then one CH3 alkyl group is present with the second carbon. That is why we have to put a straight line with the second carbon atom. And with the fourth carbon, another CH3 present. To show it, we have to stretch another line with the fourth carbon atom. I hope you understood from this figure how to draw the skeletal formula in organic chemistry. Well, now we have learned about molecular formula, structural formula, displayed formula, and skeletal formula. Let's clarify the idea of all this type of formula. First, butanoic acid. Its molecular formula is C4H8O2. By simplifying the formula, we will get the empirical formula, that is C2H4O. Well, displayed formula is a bit easier than structural formula for drawing. In butanoic acid, 4 carbon atom present, so 1, 2, 3, 4. And we know that the functional group, I will discuss more about functional group in my later slides. Functional group of carboxylic acid is COOH. So this COOH, that means CO and OH, these two functional group present here that is showing in the figure. So this spread formula of butanoic acid can be drawn, can be written in this way. And after drawing the displayed formula, it will be easy for any student to write down the structural formula. So here the structural formula will be CH3, CH2, 2 times CH2 will be repeated. That is why 2 is put here. Then at the end, COOH. The skeletal formula of butanoic acid again can be shown in this way. As I mentioned, that carbon and hydrogen will be omitted from a skeletal formula, but we must have to show the functional group. The functional group, that means with this carbon, CO and OH is also present. This hydrogen atom is a part of this functional group. That is why you cannot omit this hydrogen from here. Okay. In the similar way, octane, all different types of formula of octane can be shown according to this figure. I'm not going to explain it. If you understand one example, then you should supposed to be able to understand others as well. Then pentane, 2-methyl butane, cyclohexane. This is a cycle, cyclohexane. So skeletal formula of cyclohexane will be like this. 1,2-dichloroethane can be shown in this way. Well, next slide. Functional group. Functional group is a very important group in organic compounds because functional group will determine the chemical properties of the organic compounds. That means chemical properties include chemical reactions especially. Homologous series, we are familiar with this term, we learned it in O levels. If several atoms can be expressed with the same general formula, then those groups of the atoms are called homologous series. Between two successive compounds of a homologous series, there is a difference, CH2. You can see that methanoic acid, ethanoic acid, propanoic acid, these are in the, there are differences CH2 between two successive molecules. In a homologous series, functional group will determine the chemical properties, but the other part, except the functional group, the other part of these compounds will determine the physical properties. For example, here, if the number of carbon atoms are more, all the compounds contain COOH, that is functional group. But if the number of carbon atoms are more, then their melting point, boiling point will be more as well, and their solubility will be less gradually. Okay, I'm going to change my slide. Now, let's see about the structure of different types of organic compounds. First, alkanes. Alkanes contain carbon-carbon single bond, as we know, and its functional group structure can be shown in this way, RH. R is called alkyl group. Its general formula, CnH2n plus 1. That means if one hydrogen is short from an alkane, that is alkyl group. So RH can be the functional group structure of alkanes. Then alkene contain carbon-carbon double bond. Here you can see that in the formula R1, R2, R3, R4 is used. R actually shows the alkyl group. It can be hydrogen or any alkyl group. Halogenoalkane contains halogen atoms, that means group 7 atoms, which is generally expressed by giving X. It can be chlorine, fluorine, chlorine, bromine, or iodine. For example, 1-chloroethane is an halogenoalkane molecule. Alcohol is functional group structure is ROH. Displayed formula is showing here. OH is the functional group of alcohol. R is alkyl group. So functional group structure of alcohol can be shown in this way. Aldehyde is another type of organic molecules which contain CHO as functional group. With this CO, one hydrogen must have to be joined to make sure that this is an aldehyde molecule. Its general formula, its displayed formula is showing here. Well, in naming, like alcohol, always the ending is all, like ethanol. But in case of aldehyde, it will be L, that is ethanol. Then ketones, its functional group is CO. The difference between aldehyde and ketone is ketone does not contain any hydrogen atom with CO. And in ketone, CO will present always in the middle of this molecule, anywhere in the middle of this molecule. But in aldehyde, CHO is always present with the terminal at any terminal of that molecule, not in the middle. And here the ending is always 1. For example, propanone. Then carboxylic acid. Carboxylic acid is the type of organic molecule which contain two functional groups together. Excuse me. CO and OH. So together we read it COOH. Here the example of ethanoic acid is given. Amine is not included in age level syllabus, so I'm not going to show it here. Well, general formula is a very important character of homologous series. Homologous series can be shown with one general formula. If we put here, like for example, halogenoalkane can be shown with this formula, CnH2n plus 1x. As I already mentioned, X is an haloatom, that is, it can be fluorine, chlorine, bromine, or iodine. So if we put n is equals to 1, 2, 3, 4, then we will get different halogenoalkane molecules. The example of chloroethane is given here. Here N is 2 is put, so we have got C2H5Cl, which is called chloroethane. Sorry. Well, so you have to match this left side with the right side. First one is RCOOH. This structure is applicable for carboxylic acid as it contains COOH. Carboxylic acids are the organic acids which must contain this functional group COOH. Then here you can see that CHO is present. That means it should supposed to be aldehyde. Then RX will be halogenoalkane. This is ketone. ROH is alcohol. Well, correct. Well done. Well, I'm going to change the slide now. Here in this chapter, we have to learn about the classification of isomerism. We know about isomerism, we learned it in O level a bit, but here we have to learn more about isomerism. We know that if atoms can be arranged in different ways with the same molecular formula, then those are called isomers. So isomerism, we are familiar with structural isomerism, which we have learned a bit in O level. But there is another kind of isomerism that is called stereoisomerism. Again, structural isomerism can be classified into three types, that is chain isomerism, positional isomerism, and functional group isomerism. And stereoisomerism is a different types of isomerism. It is related with the arrangement of the atoms in the different arrangement of the atoms in the space. I will explain it more in my later slides. Well, first, chain isomerism. You can see the examples. The one formula, C6H14. This is the molecular formula. With this molecular formula, we can arrange atoms in three ways. One is a straight chain, and another two is branched. So these three are isomers that we know, but we have to understand that these types of isomers are called chain isomers, as the chains are different. First one is straight, second one is branched, third one is also branched isomers. So these types of isomers are called chain isomers. Then positional isomers. This is very interesting. You can see from the examples, all have the same molecular formula, that is C5H11Cl, but here you can see the position of the chlorine atoms are different at different molecules. The first one, chlorine atom, is joined with first carbon, that is 1 chloropropane, then 2 chloropropane, and 3 chloropropane. It depends in which position the chlorine atom is joined with carbon. So these types of isomers are called positional isomerism, as the position of the chlorine atom is different in this molecule. Then more examples. For alkene, all are hexene, general formula molecular formula C6H12. But you can see the position of the double bonds are different in different molecules. In first one, double bond is present with the first carbon, so it is hex 1 in. The next one hex 2 in, and third one hex 3 in. So as the position of the double bonds, as I already mentioned, are at different positions, so these are called positional isomerism. Then another type of structural isomerism is functional group isomers. You can see the molecular formula of both the molecules is C3H8O, but we can arrange it in different ways, so they are isomers. But what type of isomers are they? That is the question. In first molecule, you can see that functional group is OH. Its name is propanol, so this is alcohol. So functional group is OH, but in the second molecule, you can see the functional group is not OH. It is O. The two sides of the oxygen, there are two alkyl groups. So these molecules are actually ether. So the functional groups are not the same in these molecules. So these examples are the examples of functional group isomerism. I'm going to change the slide now. Well, there are few quiz type questions here. I can introduce it. What type of isomers are these? You have to choose any from these three options below. So here you can see that the position of the double bonds are different. All are butene, but the position of the double bonds are different. So this will be positional isomers, right? Next, these two are isomers, no doubt. Their molecular formulas are same, but one is a straight chain, another is branched. So it will be chain isomers. This one, position of bromine atom is different. So it will be positional isomers. These two are branched. And here we can see these are chain. Chains are different. Does not look like same. So it is chain isomers. Next one. Here functional group is different. Here the functional group is COO, and in the two sides of the CO there are two alkyl group. So this is a star. And this one is carboxylic acid at COOH is present. So this is carboxylic acid. So these are functional group isomers. Well done. Well, then another type of isomerism, stereoisomerism. This is new for you. You didn't get any idea about stereoisomerism in O levels. Stereoisomers actually occur when there are double bond present in between two carbon atoms. If there is carbon-carbon single bond present, then we have to consider that single bond as a stick, like there are two bearings present at the two terminal of this stick, so that the carbon can rotate. Both the carbon can rotate. But if any double bond is present between two carbon atoms, then due to the presence of the pi bonds at the up and bottom, electron cloud is present, so the rotation will be restricted. Well, as the rotation of the carbon atoms will be restricted with these two carbon engaged in double bond, so we may see some differences. Look at this tree structure. It will be easy for me to make you understand giving the examples. If we consider there is a single bond present instead of having any double bonds, then these two molecules we may consider same if any single bond present, because both the double bonded carbon is joined with the same atoms and same species. Like this carbon is joined with one hydrogen and a CH3 group. This carbon also contains a hydrogen and CH3 group. This carbon contains a hydrogen and CH3 group. This carbon also contains hydrogen and a CH3 group. But the problem is, if as a double bond is present here, so the rotation will be restricted. When the rotation will be restricted, you cannot consider both the atoms are same, because here CH3, in this molecule, CH3 remain present with the same side of these two carbons. And this is not like this one is not same like this one, because here rotation is restricted. So if CH3 is not in the same side, then these two have to be considered as different molecules. In the space, their arrangements are different. Their structures are same, but their arrangements are different in the space. So these two are called cis-trans isomer, geometric isomer or cis-trans isomer. If same atoms or species are present with the same side, then that is called cis. And if they are present in the opposite side, that is called trans. And these two molecules won't be superimposed. Well, I'm going to change the slide. Here are the examples. Cis-butene, because the CH3, these species are in the same side of this two double bonded carbon. That is why this is cis. And this one is trans, and the CH3 are in the opposite side. So it is called cis-1,2-dichloroethene, and it is trans 1,2-dichloroethene. Well, I'm going to change the slide now. But what happens if carbon-carbon double bond present and 4 different species are available with the same molecule with the 2 double bonded carbon? Then how will we name it? The previous example we have seen 2 different types of species present, but here 4. Now in this case you have to find out the priority group for each carbon. Here in the example with this carbon, we have to consider which one is priority group. That means iodine, between iodine and bromine, which one is priority group? Priority group will be determined from the mass. If we compare between iodine and bromine, the mass of iodine is more. So iodine is the priority group. Similarly, with this carbon, fluorine is the priority group. So if the priority groups are in the same side, that is cis. If the priority group are in the opposite side, that is trans. It is also called EZ type. EZ. That means cis types are called Z and E types are called trans. We do not need to mention E or Z. In Cambridge, instead of using EZ notation, if we write cis or trans, then that will be okay. Here actually more explanation about EZ is given. We do not need to go through this EZ notation here because Cambridge will allow cis-trans naming, as I have already mentioned. Stereoisomerism is basically 2 types. One is geometrical, it is also called cis-trans. Another one is optical isomerism. Well, in case of optical isomerism, we must have to have a chiral carbon. Chiral carbons are those carbon which contains 4 different types of species around it. You can see that in this example, this carbon contains hydrogen, CH3, NH2, COOH. So 4 different types of species surrounded with this carbon. So here in this carbon is called chiral carbon. These chiral carbons are not superimposable. It's very difficult for me to explain the superimposable using these slides, but if you see your mirror image of right hand in front of the mirror, then it is not superimposable of your right hand. Your mirror image of your right hand can be superimposable of your left hand. So when any molecules are not superimposable, then their mirror image and that molecule are called optical isomers. If we pass a plane polarized light through the solution of this optical isomer, then one molecule will rotate the plane polarized light towards clockwise direction, another one will rotate anti-clockwise direction. Well, that's all for today. I hope you have understood this chapter, Introducing Organic Chemistry. We will see you soon in another class. Thank you.